Boom! Okay, so we're looking at this ILD here. This is a motion interactive lecture demo. And what we have here, what we're going to be doing in a second, is I've got this cart. Now these are super fancy carts. They're nearly frictionless, okay? So you know how like Hot Wheels cars, whenever you're a kid, you pushed them and they kind of like stopped? These have sweet wheels. And do you hear that? Barely, probably not. The AC unit's too loud. These things just spin and spin and spin, okay? So they move nearly without friction. There's some friction there, but they're as good as it's gonna get, okay? This is a track. Vroom, vroom, the car can slide on the track, just like whenever you were 5 playing with cars, okay? I've taped to it a fan. Now this might be a little loud for you watching this, but the fan goes brrr, just like that, and I can turn it on and off, okay? That's all this is. It's a car on a track with a fan. We have back here a motion detector, and it works like a sonar system. What it does is whenever I click the button, it'll go and it'll shoot out a sound wave, which will bump into the fan, and it'll bounce back. The motion detector times that, and because it knows how fast sound moves, it knows the sound's velocity, the sound speed, it can say, hey, look, a speed divided by a time, a time divided by a speed, rather, is going to give us a distance, okay? So we're able to find a distance that way. Did I do that wrong? A velocity multiplied by a time. Duh. Velocity multiplied by a time is going to give us a distance there. So it calculates a distance using a little bit of math and a little bit of technology, okay? What we're going to start off with, though, on this ILD sheet that I have, and if you're looking online for this, it's in the Unit 2 Notes section, or it's just in the Canvas. There are 4 demos here. We're going to try to get through all of them today. We're going to see how it goes. But in the first demo, what I'm going to do is this cart is going to be sitting right here, and I'm going to hit start on our collection thing. So it's going to collect the positions, and it's going to calculate the velocities. And all I'm going to do is I'm just going to push the cart. Okay, I'm going to give it one little push. The cart's going to go down the track, and then I'm going to stop it at the end. What I would like you to do right now is I'd like you to predict what the position and the velocity graphs are going to look like. Okay? And we're going to assume that moving away from the detector is the positive direction. That's just how these detectors are set up. They're set up so that moving away from the detector is positive. So you at home, I'm going to stop this video right here. I'm going to give it a pause, so whenever it comes back, it's going to zip into a new spot here. And you put down your prediction on what's going on, and then we'll take a look at it in a minute. Okay, we're back. Okay, so now we just made our predictions. We've got a lot of curves going for the position graphs and some curves and straight lines for the velocity graphs. I'm going to start this collection, and then I'm going to push this, and then I'm going to try to catch it and stop the collection here, okay? So, everybody ready? Here we go. We are collecting. Okay, so let's get a zoom in on these time periods here. Okay, so what are we looking at here? Does this look like anything we have predicted? Not exactly. Okay, so what are we looking at? Well, it kind of starts flat. What was this flat starting region? Well, here, let's just run it again. Let's figure it out. So it looks like this flat starting region was just, I hadn't pushed anything yet. It was just like kind of ticking on. And if we look at the actual number here, 0.18 seconds, 0.18 seconds is, or 0.18 meters is generally right about here. And it's kind of where the cart starts. The sensor thinks that this is the 0 position, the beginning of the ruler, the meter stick, and we're about 0.18 meters away, 18 centimeters. So that's our starting position. And then as I push it and it goes away, that position is increasing. And if we look at this, this position is increasing on a straight line with some positive slope. So that slope is the velocity, and it seems to be constant. If I look down here, our velocity is 0. We haven't pushed it at all. And then all of a sudden, bang, I push it, and now as it's moving along, this velocity is constant and positive until it gets to the very end here, in which it falls off the end of the ramp, and boom, that's the end of that chapter, okay? So if this is just the beginning here, this is kind of like nothing. This is kind of garbage data. What we really want is the push and then the go. This right here and this right here should go onto our keep sheet. This is actually what is happening. As this cart moves with some constant positive velocity, it's going to have a constant positive slope, so something sloping upward at a same rate, no curves there. And our velocity graph, because this velocity is constant and positive, it will just be a flat horizontal line. Now, can you think of any examples of when you may have had a constant positive velocity in real life? I know a bunch of you are dangerously on the road driving right now. How can you get your car to have a constant positive velocity? I could press the gas, but when I press the gas, what happens? I speed up. That's not constant, though, is it? I'm speeding up. Cruise control! You put that sucker in cruise control, you're hitting 60, and that's it. You don't have to think about it again. That is a constant positive velocity. I like it whenever I go into supermarkets, and you may have done this too. You put some items in your cart so it gets nice and heavy, and then when nobody's looking, and this was easier to do before COVID, but you would kind of push your cart a little bit, and then you'd jump on it, and you whee, and you kind of drift along the aisle, and then you kind of knock over a bunch of cereal boxes, and then you're running away. That is the same idea. You've pushed that cart, you've given it some initial velocity, you've hopped on board to have some fun, and now it's moving at a constant velocity, okay? So that is our first example here. What we're going to do now is we're going to flip things around. Now, the cart's going to start over here. And I'm going to do the same thing. I'm going to slap the start button down here. I'm going to push the cart, but now the cart's going to be moving this way. It's going to be moving to the left and approaching our sensor. So what I'd like you to do is either on this prediction sheet, or if you have a blank piece of paper, for a position and a velocity graph, how do you think those graphs will look? For position and velocity, whenever I just push this cart and it's coming to the left here, what will that look? Okay? What will it look like? So I'm going to pause this video now, and then we're going to have a discussion here. When we come back, we'll see what that looks like. Okay, so we're here looking at the second example here, where I push this cart towards the detector. We've discussed some ideas. We've got a lot of straight lines this time, some based off of what we've done previously. So let's take a look at what's going on here. So I'm going to start it, push it, and then stop it before it knocks everything over, okay? So here we go. Okay, so let's look at this. What do we got here? Anything up match the board? Well, Jimmy's kind of does.
That was the opposite.
But like in the wrong direction. We were like going backwards in time. Okay? So once again, it looks like what we have in this beginning segment here is I was over here dealing with all of this stuff in the computer, and then I had to scurry over here and then push it. So it looks like this is some dead time that doesn't really matter for us. Now it looks, and then we see the velocity 0 here, we're just at rest. That means this little push on the bottom that I gave the cart, that's when the cart is speeding up right there. That's our push. And then now we see that our slope up top right around this point, our slope up here is nice and constant as this goes down. So we start up top. Okay, we're past a meter here. And if we look at where the cart actually started, you know, here's our meter stick. Our cart started past a meter stick. We're at like 1 point something. And that's why on this graph, we see we start just a little bit above 1. We actually start about 1.1, 1.07. So we're just past 1 meter. And then whenever this starts decreasing its position, it does it at a constant velocity. And that velocity is negative because this slope here is coming back down. And then at the end here, this is when I just stopped the cart and then I stopped the computer. We also see for our velocity graph that we once again have a flat line, but it is in the negative direction this time. Last time we did it, and if we look at data set 1, or maybe data set 2, data set 2, we looked at the last one, our velocity was positive up top because I pushed it in the positive direction. Now our velocity is the same idea, but it's negative. Okay, it's just negative down here. Now, if you're looking very carefully and you're questioning me, you might say, Mr. Botzer, it looks like our velocity is actually getting a little bit closer to 0. It looks like it's kind of rising down here. Well, remember, I said that these carts are almost perfectly frictionless. there's a tiny bit of friction, and that is why our velocity goes from like a negative 0.4 to a negative 0.355. So because we are getting closer to 0, the cart is slowing down after I push it, but it's not slowing down much because they're nearly frictionless here, okay? Boop. So that's what we kind of see with that. So that was our second demo here. Now what we're going to do is we're going to spice things up a bit. Now, in demo 3, we're going to look at velocity graphs and something we haven't taken a look at yet, acceleration graphs. Now, what I'm going to do here is I'm going to put this near the detector here. I'm going to turn the fan on, so it's spinning up really fast. I'm going to let it get to the max fan speed, and then I'm going to let go of the cart. Okay? And the fan will push the cart this way. Okay? So the fan will have a constant force, a constant acceleration acting on the cart to push it along the ramp here. What I'd like you to do is I'd like you to diagram, take a guess, think about it. What do you think a velocity graph for this would look like? And I know we haven't talked about it yet, but I'd like you to take a shot anyways. What would an acceleration graph look like when this fan is pushing the cart? Okay? So for you, those of you at home, take your sheet or take a sheet of paper. We're creating a velocity and an acceleration graph for this setup right here. Okay? Whenever the fan is pushing the cart. So I'm going to pause the video. When we come back, we will test this out. Okay, so we're diving back into this. I'm going to turn the fan on. It's going to push the cart with a constant force down the track. And we're going to see how not the position and velocity graphs look, but how the velocity and the acceleration graphs look. So let's clear these out real quick. Oops, that's two graphs. Okay, so here we go. This might be a little loud at home, so I would recommend you turn down your headphones real quick. 2, 1. Okay, you should be turned down. Here we go. I'm turning the fan on. Collecting! Okay, so let's see what's going on here with our data. It's a little bumpier this time. It's a little bumpier. The fan, whenever it turns on, it wants to rotate the cart, and the actual ramp itself pushes the cart back, so it's kind of down the track. So it's not perfect. There's a little bit more friction here. But if we take a look at this, this was when I was just holding onto the cart, right? So we can kind of ignore this. And then when I let go, what happens here? Here, let's get some zooms on this. When I let go, what happens here? It looks like our velocity, what we care about, is kind of this region, because down here, this is whenever the cart kind of fell off the track, right? And I had to go catch it. This looks to be a rather straight line, right? From about here out to here. That looks to be fairly linear. And, hey, look, one of our predictions was actually a nice linear line, going from an initial velocity of 0 out to some final velocity. Now, our acceleration graph here, oh boy, it looks kind of freaky. Let's ignore this at the end, because that kind of is whenever everything stops. And let's just look at this middle section here, okay? Well, it does have some ups and downs here. Notice that all of these acceleration values are positive. And that makes sense because the fan is pushing it into the positive direction. And if the velocity is going to increase in the positive direction, it needs to accelerate in the positive direction here, okay? The bumpiness to them, let's see if we can pick out why these bumps are occurring. Let's look right here at around this 2.5 second mark. Well, that corresponds to these velocities up top. If we recall, the slope of a velocity graph is the acceleration. And if we notice, like right here, notice how there's like, it actually is a decreasing velocity for this tiny moment in time. That's just what the detector happened to calculate based on the position. Because of that, it's going to try to make some negative acceleration here. And if you actually look, there's like a little pixel there that starts to go negative. But because this graph on the velocity gets a little bumpy, that means the acceleration is going to be even bumpier. But in theory, this should be a nice flat acceleration line the whole time. Let's just try to run it one more time to see if we get some cleaner data here. So let's go ahead. Watch your ears. So if we just look at this good section right here and right here, we notice that's a pretty constant acceleration we have. When something weird happens, something weird happens. But we should be having a nice, flat, positive value for our acceleration. So for our velocity graph on our keep sheet, we can have something starting at 0 and going in a nice positive slope forward. For our acceleration graph, we're going to have something that just is going to start at some positive. And actually, this one right here, that's what we want. That was our good prediction. And this here was our good prediction as well. So look at that. We got it. Okay? Now, for our last demo we're going to do here, it's a combination of a push and the fan. So what I'm going to do is I'm going to turn the cart around. Okay? And what I'm going to do is I'm going to push the cart this way. But I'm going to have the fan on when I do it. So the fan is going to be blowing back in the opposite direction. Okay? Draw what you think the velocity graph will look like, and draw what you think the acceleration graph will look like for that. Okay? And while you're doing that, for our last example, whenever we were kind of speeding up here in this way, what was mentioned before stepping on the gas pedal, that's a perfect example of what we just saw there. Right? When you step on the gas, it's like you're turning the fan on in the car, or you're getting the engine to run harder, and you're pushing the car faster down the road. So that's a good example of what we had there. Okay? But for this one, we are giving the car an initial push, but that fan is blowing back in the opposite direction. So what do we think our velocity graph and our acceleration graphs will look like? Plot those out, see what you get on our hand this in sheet, and then we'll come back in just a second and take a look at what is actually occurring here. Okay, so for the complicated demo, I'm going to turn the fan on so it gets full speed. It's blowing this way towards the detector. I'm going to start the detector, give it a little push, and then we'll see what happens. Okay, so watch your ears. Here comes the fan. Okay, so let's look at this. Wow, we have a very long and nice and straight line here through the center. This is probably the best collected data we've seen of the day. Everything in the middle here was, or everything in the beginning was when I was holding it, but then it looks like this right here was the initial shove that I gave that cart. Once that initial shove has been given, though, that cart has some velocity, and it then begins to lose that velocity the whole way out. If we take a look at our acceleration, we see that there's initially this big positive bump. That's me pushing in that positive direction. But then afterwards, because that fan is blowing back, we see this constant negative acceleration down here. And this is a really nice, pretty flat line down here for the constant negative acceleration. Just like we saw a constant positive before in data set 6. We had that constant positive up here. Now we just have that constant negative because it's blowing back in the opposite direction. So that's really cool. And then here at the end, we see I'm catching things, so they're going back to 0. There is a really interesting point right here in the center where this line passes the x-axis. Our velocity was 0. What was happening whenever, what was like physically happening to the cart here when our velocity was 0 like that? It was just not moving for a second. We could also call that, what else was going on with the cart? It was stopped, and then what happened? It went the other direction. We call that a change of direction, or a turning point. So when that cart was moving here, it slowed down, it stopped, and then it came back. Right there where it crosses that x-axis, that for us is a turning point, and it allows us to know that we're now moving in the opposite direction there. Okay? So that's everything that's going on with this. I hope you enjoyed that ILD, and take it easy. We'll do more of these throughout the year. Make sure you take a picture of this and upload it into Canvas. Adios!